use that book. And yeah, we could do it as the night class. I'm fine with that.
Probably benefit me to go through it.
Probably what?
It would benefit me to go through it again.
Well, of course.
Now that
Someone who's gone through it 10 times would be benefited by going through it again.
yeah.
Yeah, real analysis is a pain. Hard to get good intuition for all the things going on. Anyways, let's jump into today's material. We got to variants of Turing machines. That's the thing we talked about last time. Or that's what we were just introducing last time. So let's really quick do a recap before we jump again into this material. Do a recap first off by reminding ourselves what exactly a Turing machine is. So a Turing machine is a 7-tuple. Q, sigma, gamma, delta, Q not, Q accept, Q reject, where everything's basically what you expect. Q is a finite set of states. Sigma is the input alphabet, where remember our blank symbol is not allowed to be in the input alphabet. The input alphabet is basically the alphabet we use to generate strings that we're ultimately going to accept. Right? We'll do a concrete example and come back and state what each of these are. Gamma is the tape alphabet, where the empty symbol has to be in the tape alphabet, because remember, when we fill out our tape, we put our input string, our tape's infinitely long, and so from there on out, it's just blank symbol, blank symbol, blank symbol. So that always has to be in our tape alphabet. And our input alphabet has to be a subset of our tape alphabet. We have to be able to write our input on the string. And then our transition function, it takes a state and an input symbol, and it spits out the new state to go to, the new tape symbol to write, and whether we move to the right or move to the left. Remember, our head can move to the right or the left in a Turing machine. With a push automata and a finite state machine, we always just move the head 1 unit to the right as we read. And we either accept it or reject it when we reach the end of our input. This machine, we have an explicit accept state. We only accept if we go into that state. And we have an explicit reject state. We only reject if we go into that state. And we instantly reject in those states. There's no such thing as going into the next step state, then out, then back in, then out, then back in. Once you go into the accept state, you accept, period. And then finally, Q naught is our start state, Q accept is our accept state, Q reject is our reject state. So, coming back to us, and let's draw out an actual diagram of one of these things to remind ourselves of how they function. So we're just going to construct the Turing machine whose language is 0 to the n, 1 to the n. Now obviously we don't need a Turing machine to do this, we could do it with a push-down automata. I just didn't want to do a complicated language since we already did a bunch of examples last time. So let's go back to this simple example and remind ourselves of how we do it. So we start out in some circle state, right? Well, first let's go over our strategy. So our strategy is, we're going to start out with our tape. Our tape's going to start out populated by some string that's 0 to the n, 1 to the n potentially. And then we're going to have infinitely many blank symbols after that. Sorry. We usually draw that to let us know it goes on infinitely that way. Our strategy is going to be, our head is going to look at a 0, it's going to replace it with an x, and then it's going to move to the right until we see a 1, and replace it with a y, and then go back and replace our next 0 with an x, 1 with a y, 0 with an x, 1 with a y, keep doing that until we run out of zeros. Once we run out of zeros, then we're going to go through checking our tape, make sure that there's no 1s left over. If there's no 1s left over, then we had 0 to the n, 1 to the n. If there's any 1s left over, then we don't do that. So that's our strategy. So let's start out writing our machine. So here's our start state for our machine. Here's Q naught. And our head is going to start right here at the beginning of our tape. Our tape in the Turing machine always starts out populated with the input string that we're reading. So what are we going to do first?
Set the 0 to an x.
Yes, we're going to replace the 0 with an x. So here's what we write. We write what input symbol we're reading on the, or what tape symbol we're reading, 0. What we're replacing it with, x. And then which way we want to move. Do we want to move to the right or the left?
Right.
Here we want to move to the right. And that gets us to this state. So we start out here. Sorry, that column's probably hard to see. We start out here, we read a 0, replace it with an x, move to the right. So we read the 0, replace it with an x, and move our head to the right. Now what are we going to do?
Read a 0 and then loop back.
so now we're going to stay in this state. Every time we read a 0, we're going to write a 0 and move to the right. So read a 0, write a 0, move to the right. Which brings us back to this state. Read a 0, write a 0, move to the right. Read a 0, write a 0, move to the right, which gets us here. Now, we often do this where we want to read and write the same symbol. If we're going to read and write the same symbol, we just write the symbol. So, read a 0, move to the right. Same thing. Okay, now we see a 1. What did we want to do?
Read a 1, write in a Y, and then move to the left.
Perfect. So if we read a 1, we want to replace it with a Y, and we want to move to the left. So now we mark this with a Y, and we move our head now to the left. Okay, now what?
Now we loop, read a 0, move to the left.
Perfect.
Read a 0, write to the 0, move to the left.
If we see a 0, we just move to the left.
Yeah, okay.
So that takes us all the way back. Eventually we're going to see an X. Then what do we do?
If you read an X, move to the right. Wait.
Move to the right and then after
just
that
go-
replace 0 with the next.
I would
Right,
actually.
so we're going to go back to this state.
Yeah, go back all the way over there.
Yeah, so we're going to go back to this state, and we're just going to read an X and move to the right.
Yeah.
So we read an X, move to the right. That brings us back to this state. Here, we see a 0, replace it with an X, move to the right. 0, replace it with an X, move to the right. Then we move right through all our zeros, which brings us to a Y. Okay, now we're in this state. What do we do when we see a Y?
Read and write a Y and move to the right.
Perfect. We read and write a Y and move to the right. Puts us right here, so now we're looking at a 1. When we see a 1, we replace it with a Y and move to the left. So it becomes a Y. Now we're in this state. We move,
So read and Y, move to the left.
read a Y, move to the left. Which brings us over to this state.
Which now goes into.
Now we read all our zeros moving to the left until we see an X. Then when we see an X, we move to the right. And we're there again, right?
And then we repeat that cycle.
Yeah, so once again, going from here to here, we replace this with an X and point our head here. We move to the right through all our zeros until we get to a Y. We move right through all our Y's until we get to a 1. So when we're right here, we now take this transition, replace a Y, or the 1 with a Y, move to the left through all our Y's, move to the left through all our zeros. Once we see an X, we move to the right and restart. So now we're right there. And then we go through this process one more time. Once again, we're going to replace that 0 with an X, which puts us here. We're going to move right through all our Y's until we see a 1. We're going to take that 1, replace it with a Y, and move to the left. So now we're here in this state, looking at that Y. We move left through all our Y's until we see an X, which puts us here. Now here, oh, and then we move to the right. So now here, we're reading a Y in this state. Now what should we do?
Okay, so if you read a Y and then you go all the way to the right and you read an empty, meaning there's no more, then you know that you're accepted, so.
Right, so if we see a Y here, we can move to the right, to this state.
And then now you gotta cycle reading a Y, moving to the right.
Perfect. Let me put that loop on the other side. Here, every time we see a Y, move to the right. So moving to the right, until we eventually see a blank symbol. Then what do we do when we see a blank symbol?
Yeah, if you read a blank, then it's an accept.
If we see the blank symbol, doesn't matter which way we move, then we go to our accept state. Now, if we would have seen a 1 here instead of a blank symbol, so after we moved right through all our Y's, if we would have seen a 1, we would have rejected.
Right.
So it's understood from our diagram, we never actually draw the reject state. We could come over here and I could say, here's my reject state, and draw all the transitions to my reject state. The reason we don't do that is because the majority of our transitions are reject transitions, and that would make our diagram a mess. So it's understood if my transition isn't explicitly written on here, then you go to the reject state and the machine just rejects. So that's just understood. So there is a reject state. There's one and only one reject state, one and only one accept state. We just don't bother drawing in the reject state because it makes a mess of our diagram and hard to reason about.
Now with computation, can you do any, can you basically program anything that we can program today with just a Turing machine?
Yes.
Okay. Just want to make sure I got it right.
Yeah. The stupidest, simplest Turing machine can solve any problem that any quantum supercomputer could solve with enough time and enough memory. So better computers could solve it faster, more efficiently, but they can't solve fundamentally new problems.
Okay.
When you were explaining the definition of a Turing machine, and you talked about like how it generates a string, like.
Did I say generates? It just recognizes a string.
Right.
never
It
generates.
comes on the tape, and then we recognize it.
Right.
Okay.
The tape starts out populated with the string,
Right.
and our job is to say yes or no.
Okay.
But it could just be an infinite string of blanks that you then fill in with all your information.
Well, no, you start by putting a string on the input tape. So I start by putting on that tape something like 0, 0, 1, 1. And I put that on the tape. And then I let the machine run. And the machine running, it's either going to say accept, or it's going to say reject, or it's going to run forever. One of those three cases.
Mm-hmm.
But if it says accept, then it recognizes that string. That's what it means for a Turing machine to recognize a string. It said accept when we fed that string as the input.
Okay.
Okay, so now let's remind ourselves of the difference between a recognizable language and a decidable language. Do we remember the difference?
Something to do with whether or not we can tell if it's going to be infinite or whether it is or it isn't.
So a recognizable language is a language that a Turing machine will accept all the strings in the language. So if A is a recognizable language, then for any string in A, if I run it in a Turing machine, it will accept that string. If B is a decidable language, then every string in B that I run through my Turing machine, it will accept. And every string not in B that I run through my Turing machine, it will reject.
If it's recognized.
If it's decidable.
If it's decided.
Recognizable means that a Turing machine can tell you if a string is in the language. It can't necessarily tell you if a string is not in the language.
Okay.
So it won't necessarily reject strings that aren't in the language, but it will always accept strings that are in the language. Decidable languages will always accept strings in the language and reject strings not in the language.
How do you account for loops, infinite loops?
So, if it's possible for my computer to go through an infinite loop, it's possible that this machine has an infinite loop, right?
Sure.
Somehow, some way, we set up a process because we weren't being smart that causes this to loop forever.
Okay.
And so, how's the right way to say this? Here's a better way to say it. If you know that a Turing machine will recognize some string, if you know it will accept that string, then you know given enough time it will eventually say accept. Right? If you don't know whether or not it will accept that string, then if your computer's taken a long time to say accept or to say reject, you don't know, did it go into an infinite loop? Or is it just taking a really, really long time to figure this out? And so maybe your computer runs for 1,000 years and it needed 1,000 years and 1 second to solve the problem. And you unplug it after 1,000 years thinking, well, it's impossible. So there's no way for us to distinguish between, is the computer never going to spit out an answer, or is it just taking a really, really long time to spit out the answer? And there's no way for us to distinguish between those two things.
Right.
And so that's kind of the difference between a recognizable and a decidable.
Meaning it recognizes the infinite loop, but it never can say that it will finish.
It's like if you gave me, let's say I built a Turing machine to recognize all the integers, right?
Okay.
So if you gave me something that was an integer, then eventually say that my Turing machine is just stupid and it's checking, is it 0? Is it 1? Is it -1? Is it 2? Is it -2? And it sits there and it iterates on that forever. If you give me something that's an integer, like 10 trillion, then my Turing machine is going to take forever to finally accept that thing, because it is an integer.
Yeah.
Now what happens if you give it something that's not an integer, like pi? Now my Turing machine accepts 0, 1, -1, 2, -2, 3, -3. Now it's just going to run forever.
Okay.
So I will recognize your language, your set of integers. If you give me an integer, I will accept. But if you give me something not an integer, there's no guarantee I'll reject it.
Right,
So that, in that case, that would be a recognizable language, not a decidable language. I can tell you, yes, it's in there. I can't tell you, no, this thing's not in there, if I build it that way.
so what about decidability?
So decidability would be if I built some machine that was able to determine, always and forever, yes, it was an integer, or no, it wasn't an integer.
So if your machine goes into an infinite loop in any case, it's not decidable.
Well, when we say that a language is decidable, we mean that there exists some Turing machine that can decide it. When we say it's recognizable, we mean that there exists some Turing machine that recognizes it. I was just trying to give you intuition for how the machine might work, and why it might be able to say, yes, it's in the set, but not necessarily be able to answer, no, it's not in the set.
Okay.
Okay, so recognizable versus decidable. A language is recognizable if we're guaranteed that there's some Turing machine that would say yes to every string in the language. It's decidable if we're guaranteed that there's some Turing machine that would say yes to every string in the language and no to every string not in the language.
You could divide this up into almost all problems that we program and put into our
Programming outside of recognizable, we no longer care. So if we go back to our bullseye, we had problems recognized by finite state machines. Then we had problems recognized by push-down automata. Then we have, so this is finite state machines. This is push-down automata. This right here then would be our decidable. A Turing machine can decide it. And this right here would be our recognizable.
What's outside of that?
Outside of that, computation theorists no longer care about. Because if your language can't even be recognized by a computer, we don't care. But there is a massive hierarchy.
But there are still problems that are outside of that, aren't there?
Yes, there are problems outside of this. There's a hierarchy. We're taking a piece of a hierarchy that's basically a hierarchy of the complexity of sets.
Right.
And so if we were in some set theory course, some advanced set theory course, then we would look at more of the hierarchy. And so there is more hierarchy to this. It's just in computation theory, we only care about this piece of the hierarchy. Because anything out here, a computer can't even recognize. Computation no longer makes sense for these types of problems.
A Turing machine or any conceivable computer?
Every computer on Earth is at best a Turing machine.
Right. But
So if a Turing machine can't do it, no computer on planet Earth can do it.
And a Turing machine is in the scope of recognizable and decidable.
Recognizable means a Turing machine can recognize the language. Decidable means a Turing machine can decide the language. Outside here, a Turing machine can't even recognize the language.
so why sorry, I'm trying to think how to ask my question. I'm wondering why computation theory is limited to Turing machines.
Because the definition of what you can compute is what a computer can do.
Right. So
So these sets are no longer computable sets.
Can you give us an example real quick of
Yeah.
what would be outside a recognizable?
Yeah, so when Alan Turing wrote his paper, he wrote his paper on what we call computable numbers. Now, the vast, vast, vast majority of numbers are not computable.
Because they're irrational? What do you mean?
Every non-computable number is irrational. But if I were to talk about the set of all computable numbers, they would have the same size as the set of integers or the set of rational numbers. You remember back to real analysis, talking about the cardinality of the natural numbers, the integers, and the rationals, how they all have the same cardinality.
And then the reals get...
And the reals are a completely different beast.
Yeah.
Well, it turns out that computable numbers are the same cardinality as the integers.
Oh, okay.
So the computable numbers are a subset of the reals, and they're all the real numbers that we have some method for generating the number.
So that essentially means we can only work with and deal with a finite number of real
Not a finite number, a countably infinite number.
Yes.
Yes, a countably infinite number of numbers are the only numbers that we can even talk about, reason about.
Of real numbers. Because we can deal with some irrational numbers.
Yeah, we can deal with tons of irrational numbers. Any number that we have a method for generating that number is a computable number. So pi is still a computable number.
Okay.
And we have formulas for generating pi to as many arbitrary decimal places as you want. But the vast majority of computable numbers, because think about it, think about the number 1 for a second. Think about how special that is. 1 is a number that's 1, 0, 0, 0, 0, all infinite decimal places after that all happen to be perfectly 0.
Right.
That's a very special number. Right?
Okay.
So all the integers are very, very, very special numbers.
Right.
So if you were to go and just start writing 1 dot and randomly pick digits, now it's impossible to build a truly random number generator. That's actually impossible. Let's imagine we poofed one into existence. And it was randomly generating numbers between 0 and 9. And we start writing whatever it generated. Dot, 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 on forever.
Okay.
So it has to run forever in order to generate our number, but our number is now generated infinitely long. That number would be an uncomputable number. There's no way for us to talk about that number. We can't write it, we can't reason about it, we can't encode it somehow. It's an uncomputable number.
But wasn't it just generated with the computer?
Well,
There's no such thing as a random number generator. We pretended one existed. Because every random number generator is really doing some computation to try to pretend to be random.
Or read from the outside world.
And we also assume that we let the random number generator accomplish an impossible task, generating an infinite number. So we're beyond physics here.
I don't know if this is an off-topic question, but I've heard that...
Here's another way to say it. Take pi and randomly change 1,000 of its digits.
Okay.
Now you've got an uncomputable number.
Right. Or randomly change one of its digits.
Or randomly change one of its digits. As long as it's not communicated somehow which digit was changed.
Right.
Right.
And you're saying there's just a whole world of mathematics outside
There
the
is-
scope of
There are
Recognizable?
far, far, far more numbers out there that we have no way of reasoning about
Right.
than numbers we can reason about, that we can somehow define. The numbers that we can put a definition to are computable numbers. And so Alan Turing's paper, when he developed the notion of a Turing machine, was on this exact topic, on computable numbers.
What's
That's-
computable?
Non-rational numbers.
All rational numbers are computable.
Yeah.
Okay. And some irrational numbers are still computable.
What?
Like pi. Pi is an irrational number. We know how to compute it. It's an infinite series, but we know how to compute it. Square root of 2, it's a rational number. It's an irrational number, but we know how to compute it. You don't know what algebraic numbers are, but every algebraic number is computable.
Wait, so now you're saying that the numbers that we can, compute until we get tired of computing or we don't want to compute it anymore, are within the scope of recognizable?
Yes.
Okay, so I'm still going.
Yes, a Turing machine could recognize every computable number.
Well, to an extent. It can, what I mean is, it can't completely recognize pi, but
It can get
essentially-
arbitrarily close
Yes.
to that number. So if a Turing machine can get arbitrarily close to that particular number, then we call it a computable number. That's exactly what we mean.
Are there physical phenomena that are,
There's no way for us to know.
well, I've heard that in like quantum physics, there are some things that people think are totally random, meaning there's a probability that they'll happen, but there's no way to really decide.
Oh, it appears to be that way based off the distribution.
Okay.
You can
So measuring the spin of an electron, if you do it 10 trillion times, almost exactly half the time it's going to come up, and almost exactly half the time it's going to come out down.
So would it be, I mean, theoretically, would it be possible to make a computer that generates something random, basing its computation off of some random phenomenon?
Yes, they do that all the time. In fact,
Kind of. So I can generate, for a 0 and a 1, yes, I guess. But now to get a completely arbitrary random number, so I guess the example I said wasn't quite good, because we were doing a finite random number an infinite number of times.
Right.
But to get a truly random number between 0 and 1 is impossible.
You're saying just go and select one.
Yes, to get a completely random number between 0 and 1, because you need infinite information to get that random number.
Right, but isn't it essentially the same thing?
No, because that's just now a binary decision between two values, a 0 or a 1, up or down. We can get that with quantum mechanics, yes.
Sure.
But now if I want a truly random number, I need to be able to generate it to infinite many decimal places. And so I would have to do my experiment with an infinite number of electrons.
But, okay, yeah,
That's the
but
impossibility.
you can get arbitrarily close to some random number.
Yep, we could get a lot of randomness. Well,
you know what's good
So,
enough
for practical use, it's essentially the same thing, right?
now,
well, what's good enough for security is if you're generating like a hash key for your SSH connections and stuff, they just measure the movements of your mouse and they say, oh, we're
Right.
random.
so they have something that they go off of, but it's not truly random.
Yeah.
It's close enough.
They just know humans are going to be random enough with the way
Right.
they move the mouse.
Random enough that
That
you
it's
can't really
unpredictable.
predict it.
But I've also generated random keys up to the billions of times, and I've never actually found it to be even on one side or the other, or get close to the center. Always lopsided, meaning the way we do random generation on our computers, which is more of an algorithm, it's not even perfect as far as that you're going to get kind of an even ratio one way or the other.
Right, we can do an amazing job at generating, for all practical purposes, random numbers. IDs, typically so you create some object in your database that has to have a unique ID. IDs, now we just generate some random thing.
Right.
And so it's theoretically possible that typically in your database, when you create two objects, that they actually have the same ID. That's theoretically possible. But the odds of it are so stupid impossible that no one actually worries about that. But we don't bother checking that when we generate objects in our database. We don't bother checking, does this object have an ID that already exists somewhere out there in the ether? We just generate a new random ID. And the odds of that being like any of the, doesn't even matter if you got a million objects in your database, the odds of it being the same as any of those are so astronomically small that no one even seriously worries about it.
Right. Okay, so what you're saying is it's possible for us to get to the perfect idea of a random number, to be able to achieve that.
Right.
But it is possible to make a selection of digits that has no pattern, not even pseudo-random, up to as many decimals as you want. that right?
There. Kind of yes, because you're trying to play on the fact that we live in this world with something called an electron, and it has this behavior. But you're not designing an algorithm that generates that thing.
Right.
A computer is not doing this somehow.
They'd have to be measuring a phenomenon.
Right. So you're thinking, yes, we could get an infinite number of electrons, line them up, or an arbitrarily large number of electrons, line them up, and measure them, generating a number as we go. But that's not an algorithm.
Right.
So it's not being computed.
Has it been proven impossible to do that? To make an algorithm that generates something randomly?
Yes, because any random number you pick, odds are it's going to be an uncomputable number.
So-
Because the number of non-computable numbers vastly outnumbers the number of computable numbers. Uncomputable numbers has the same cardinality as the real numbers. Computable numbers has the same cardinality as the naturals.
What computers normally do is they use the time where computer started.
Right.
Use
Right.
the timestamp
As a
to
seed.
create an algorithm as a seed. So, yeah.
Right. So yeah, we can do a good job at pretending to generate random numbers.
Good enough for what we need it for, I guess.
Good enough for practical purposes. But for theoretical purposes, no. A computer can't generate a random number. You can't create some algorithm to produce a random number.
So do you think that that could be a thing possible in the future?
Not with an algorithm.
Not on Turing machines. I mean a whole new type of computer that can handle that type of number.
We'd have to change what we fundamentally mean by computer. It wouldn't be a
Right.
computer,
Right. It'd be
because
something else.
by definition, a computer is this thing, and this thing provably can't do it.
Right.
So, yeah, I don't know.
The next step, what I mean is like generating something that's the next step up in the hierarchy.
We have tried like crazy to come up with something more powerful than a Turing machine, and in fact, that's our next topic here. Is, okay, so we've got a Turing machine. Is there any way that we could somehow make a Turing machine more powerful? Because you had a finite state machine, and you gave it a stack, and now you had a push-down automata. And that could fundamentally do more than just a finite state machine. And now we take a push-down automata, and we replace its stack with this tape here. You can think about it as replacing a stack with a queue. Same thing. And now you suddenly have a Turing machine.
So,
Is there something else that we could do, some power we could add to a Turing machine to somehow fundamentally make it more powerful? Right? That's a big question. The answer, roughly speaking, is nothing that we can think of. And we'll go over some examples and show that they don't really add any power. So let's go over some variants of Turing machine to try and add power to the scene. Well, one of the most simple things we might allow a Turing machine to do is allow it to stay. Rather than forcing it to move to the left or move to the right, maybe we give it the power to also stay, so it doesn't have to move. And does that somehow make it more powerful? Does that make it solve new problems that a regular Turing machine can't solve? And here's how we're going to make our arguments for these things. Because we're not going to do full-blown proofs. So what if we allowed stay? So now our transition function takes a state and a tape symbol and spits out a state, a tape symbol, and right or left or a stay. Well, we could simulate this new machine by simply interpreting an S move as a left-right move. So if I could simulate this new machine with just a regular Turing machine, then it's no more powerful than a Turing machine, because a regular Turing machine can simulate it. Make sense? And so that's roughly how our arguments are going to go.
Okay.
So let's move on to a more interesting example now. What if we make the tape infinite both ways? So we know that the tape is infinite this way. We can go this way as far as we want. What if we made it infinite this direction as well? Does that make a Turing machine more powerful? And here's our idea for how we're going to simulate this thing. Write it up here. So one way we think about, imagine a Turing machine that went infinite in both directions. Is there a way that we can simulate this with a machine that only has a tape that's infinite in one direction? So here's our idea. Pretend that for our one up here, we have some $sign symbol that marks the middle of the state. And then over here, just to make the picture obvious to us, I'm just going to say this has zeros completely to its right, and it has ones completely to its left. You with me? Actually, let's make this ABC. So letters over here, and then numbers over here. That way, it's easier to see what cell ends up where. Right?
Okay.
Now, when we populate it onto just a single tape, we're going to put our dollar sign here, and then we're going to put A1, B2, C3, etc. So, infinite both ways, first thing we do is we place a dollar sign on the far left end of our tape to signify what would have been the middle of this tape. Then, anytime we're reading the dollar sign symbol, that toggles which side of the tape we're on. So if my head's moving along and I ever come across this dollar sign symbol, then that means I've moved to the left side of the tape or the right side of the tape. When we're on the right side of the tape, we interpret any right move to the right with 2 moves to the right, and any move to the left with 2 moves to the left. Similarly, if we're on the left side, we interpret any move to the right as 2 moves to the left, and any move to the left as 2 moves to the right. Let's make sense of this for a second. So let's say that our head, we're right here on this machine, and right here on this machine. With me? So on this machine, we move to the left, so now we're pointing at A. We're on the right side, so when we're on the right side, any move to the left we interpret as 2 moves to the left. So this machine moved to the left, we interpret that as 2 moves to the left, so now our head's here. With the exception of when we read the dollar sign, then we always stop and just toggle. So now when they move to the left again, they get to dollar sign. We go to dollar sign, and now we toggle and we say, okay, now we're switching to the other side. So now, if they move to the left again, so now they're at 1. Now that we're on the left side, we interpret a move to the left as 2 moves to the right. If they move to the left again to 2, we interpret a move to the left as 2 moves to the right, so we're pointing at 2. And that's roughly how the idea works. Make sense? So, we can simulate a string or a tape that's infinite both ways with a tape that's still infinite one way. Okay, so that didn't make it more powerful. All right, what about if we give it multiple tapes? So we don't limit the Turing machine to just having 1 tape. What if we give it 100 tapes, 1,000 tapes, 1,000,000 tapes? Some k number of tapes. That's the next one we're going to look at. Make sense? So if we gave our Turing machine k number of states, then what does our transition function look like now? For our new Turing machine. So here's an example of a Turing machine we're talking about. In this case, it has 3 tapes. So if we give our Turing machine k tapes, what does the transition function look like now? It takes a state and it takes k input symbols, 1 for everywhere the head is. So if k is 3, then it's going to take a state and 3 input symbols, and it's going to spit out your new state, your new 3 input symbols, and then whether we move to the left or to the right or stay 3 times. For case the number of tapes, let's see a concrete example just to make sure it's perfectly clear. So if we give it an input, some state q sub I, and some tape symbols, A1, A2, all the way to AK, so this would be A1, A2, dot, 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 AK's right there. Those are all the inputs. Then it spits out our new state, q sub j. The new symbols that we are going to write on the tape in all those places, we're going to replace A1 with B1, A2 with B2, dot, 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 AK with BK. And then we also need to specify whether we move to the left or right or stay k times after that. So that's what the transition function would look like for this multi-tape Turing machine. One thing to note about how a multi-tape Turing machine works is it starts with the input on the first tape and all the other tapes start out blank.
Why?
It's an arbitrary choice. What did someone mean when they said a multi-tape Turing machine?
Well, they meant they had a Turing
It has multiple tapes, but where do we put the string? Let's just say we put the string to begin with on the first tape.
Are they saying that they're reading 3 values at the same time, or that they can only read from
Yes.
one tape at a time?
We're reading from all 3 tapes simultaneously
Okay.
and updating all 3 tapes simultaneously.
So you're reading 3 strings at once.
Well, we're reading from 3 tapes at once. But the input string that we're reading is just going to start out on the first tape. So this tape's going to start out reading a blank symbol, this tape's going to start out reading a blank symbol. If you want your input string to start out on all 3, you could have your machine first thing copy that string. Okay. And then you can put it on all 3. The Turing machine can do that if you want it to. It's just an implementation detail. You need to specify so that if I'm actually going to draw one of these things out, I need to specify how it starts.
Why can't it start on all 3 of them?
You could have chosen that as your definition for a multi-tape Turing machine. It wouldn't change anything. Because if a person didn't want it there, they could have their Turing machine start by replacing all of these with blank symbols.
So what's the value of starting with first string on first tape and the other tapes?
It's arbitrary. We just need to put the input string somewhere. Because a Turing machine needs an input string to accept or reject.
What? So isn't it all 3? What's the value of the other 2 tapes if they're not part of your input string?
We can still write and read from them. I can make my first operation if I wanted, make my Turing machine write that right there. And right there.
Okay.
That's perfectly fine.
So when we say multi-tape, it's not reading multiple strings at once. It's reading one string.
It has
Multiple tapes.
3 tapes that it can access simultaneously.
Okay.
Because think about going back to PDAs. Sometimes it was useful to store a little bit of information on the stack as you were going along. So maybe you're just going along here, storing some useful information here, and some other useful information here that you're going to come back to. Right? So, you can copy the string on all tapes if you want, but just as a matter of definition, we say it starts with the input just on the first tape. Okay. So here's roughly what some multi-tape Turing machine might look like. And the symbols I put there are completely random. And right now, this head's right there, this head's right there, that head's right there. Those heads don't have to be staying in sync in any way. The symbols here don't have to match the symbols here, don't have to match the symbols here. The Turing machine can change them however they want. So now how can we simulate this multi-tape Turing machine with a single tape Turing machine? And here's the way that we're going to do it. First off, we start by taking the alphabet of this thing. We add to its alphabet when we're coming over here the hash symbol. If they already had a hash symbol, make up a new symbol. Some new symbol that definitely wasn't there, the hash symbol. And for every symbol in its alphabet, so this one's alphabet happened to have 0, 1, A, and B, and blank symbol. We add to the alphabet 0 with a dot above it, 1 to a dot with above it, A with a dot above it, B with a dot above it, and empty symbol with a dot above it. So for everything in its alphabet, in our one that we're simulating over here, we're going to add all these symbols to our alphabet. With me so far? So we extend the alphabet like that. And now what do? I do a hash symbol. I write everything on the first string. Hash symbol, everything on the second tape. Hash symbol, everything on the third tape. Hash symbol for every tape that we have. Since in this case we have 3 tapes, here's my 3 tapes.
What's the value of the dot?
And now the value of the dot, I replace it with a dot above it if that's where the head is currently pointing.
Oh, okay.
Since the head here is pointing at 1, the dot there says head's pointing at 1. This one says head's pointing at B. This one says head's pointing at A. Good intuition?
Okay.
Okay. And so, fundamentally, what is our Turing machine going to do? It's going to go through, read all the symbols that have a dot above them, run it through this machine's transition function, which is going to tell me all the new symbols to write and how to move them. And then so it will go and repopulate all those. If it needs to add a symbol, something that you need to be aware that a Turing machine can do, we can shift all the symbols 1 space to the right to make more space. And that would be pretty easy. You could write a Turing machine to shift everything 1 unit to the right, right? Just copy it over, blank it out, and copy whatever you saw over, blank it out, copy whatever you saw over.
So twice the language, and then you just concatenate them all to one thing.
Yeah, but when we need space, what we're going to do is just shift all these 1 unit to the right and put a blank symbol there.
And you delete all of the empty spaces.
We probably do. Keep all the empty spaces out. I don't know if we need to. Should be fine, because if you generate the empty space with one of these, then your transition function knew what to do with it. So we don't need to get rid of empty spaces.
Well, you're going to have an infinite number, right?
Oh yeah, we have an infinite number of blanks after that.
What I mean is, if you were to just take the 3 tapes and add them onto each other, you'd have an infinite number of empty spaces in between each tape. That's what we need. Yeah, we don't bother copying these blank symbols. Yeah.
Okay, yes. But if they stuck a blank symbol in the middle for some reason, then that would be copied.
Okay.
Okay.
With a delta function, how does it look to shift everything to the right? Like to just add something and not replace something? Because don't you have to take in something from the
You'd keep track of it in your state machine. So I have a state machine that says this would be the state my next symbol needs to be an A. This would be the state my next symbol needs to be a B. This would be the state that my next symbol needs to be a C.
Right. I get that you keep track of the states with your.
You keep track of the next thing you need to write. So let's say that this is the state I go into that says, I want to, so coming into here, this is the state that says, we need to start shifting to the right. And we transition to it however. You with me? Now when I need to start transitioning to the right, I say, if what I see is an A, then I'm going to go to this one. We move to the right, but I'm going to go over here. This means that the next thing I write needs to be an A. If the next thing I need to write is a B, then I go over here. And if the next thing I need to write is a C, then I go over here.
So basically it would be a
And then this thing is going to read whatever it's replacing. So if the thing it's reading is a B or an A, then it's going to come over here. So we're going to take our C, we're going to replace it with an A, and we're going to go over to the right. Or sorry, we're going to take our A, replace it with the C, and go to the right. And now here's saying the next thing we write needs to be an A.
Right. Okay.
And so we just track it internally in the states like that. But yeah, that's just an implementation detail. If you had to think about it, I think you could figure it out. If I give you a finite alphabet to work with. But yeah, very common thing that we have to do with a Turing machine tape is shift everything starting at some point to the right. All right, so now we got some intuition for how this machine works. Let's get into a more detailed proof. So a Turing machine S can simulate a multi-tape Turing machine M. And here's our proof. Now I told you that we're never going to actually write Turing machines like this again. And when we write them out, it's going to be more like this, where we just explain the procedure rather than actually writing out the diagrams, because those diagrams get unwieldy very quickly. So we define a new Turing machine S, and it's going to equal this description of this procedure. On input W, where W is W1, W2, W3, ... Wn, so these are all the characters for our input string. First thing we do is format the input tape to represent all K tapes of M. So the tape, not tapped, the tape is of the form hash symbol W1, W2, W3, ... Wn with a dot above W1. Hash symbol empty, hash symbol empty, hash symbol ... for however many K we have empty. We good on how we first initialize the tape? Okay. Now, for each move of M, our multi-tape machine, for each move we have over here, first, over here, we need to scan S from the first hash symbol to the last hash symbol, from there to there, to the last hash, to determine all the symbols with a dot above them. And we just track that in our states. We'd have a state that said the first one had a 1, or the first tape had a dot above the 1. And the second tape had a dot above the 2, so it would blow up very quickly how many states we had. I could have a state for each of the possible combinations that we could have for all these tapes. in our state, where we track our states, like over here. So that would blow up very quickly, but we could track what all the input was. As we just go from state to state, saying this is what I've seen from the input so far. So, feel like you understand how we could read through this string, keeping track of what the entire input was in our states.
So you'd have a state for every possible string.
For every possible combination of symbols that our heads could be pointed at, but also for every possible way of generating those. Because I need to have a state that says the first one was an A, and then I need to have a state that said the first one was an A and the second one was a B. I'd also need one that said that the first one was an A and the second one was an A. I'd also need one that said that the first one was an A and the second one was a C, if those were only letters A, B, C.
But then you'd have to have...
And then for each of those, I'd have 3 coming off, 3 coming off, 3 coming off.
So
But I could track the things, since all of this is finite, since there's a finite number of tapes and a finite number of symbols on our alphabet, tracking what the input was would still be finite number of states.
Still a really big number.
Just a really big number. We don't care about efficiency, we care about possibility. Is it possible to do this?
Okay.
So, you good with how we could we could track the entire input just in the states. So, we scan over the tape from left to right to determine all the symbols with a dot above them. Then we're going to scan the tape again, this time updating each dot symbol according to m's delta function. Notice that we have to know what all the input symbols are before we can use this delta function. Because this delta function needs our current state and all the input symbols, and then it spits out all the output symbols and how to transition. And so then after it spits those out, then we can go over the tape again, updating each tape as we go. That make sense?
Mm-hmm.
So the trick there was just to get all the input information first before we run it through this function. Because you can't just run it through one at a time. Because this function needs all the inputs to spit out the output. You can't just say, give me the output for the first one, then give me the output for the second one. Okay. 3. If at any point S tries to write a hash with a dot above it, shift the entire tape 1 unit to the right from the current position, and write a blank symbol with a dot above it instead. Then continue as before. So if I'm coming along here, and I try to write on this, I try to move my head here to this symbol, I instead would move the whole tape down 1, and write a blank with a dot above it instead. Make sense? Okay, and so that is how we would simulate a multi-tape Turing machine with a single tape Turing machine.
How do our actual Turing machines work?
A lot similar.
Do they
Like
have
this?
what I mean our actual computers, like how do
Oh.
computers work?
Much different. So computers, when you actually build a computer, you're dealing with logic circuits.
Right.
And so you prove that your computer is Turing complete.
Okay.
And so you have a way of demonstrating that this is logically equivalent to a Turing machine. And therefore everything a Turing machine can do, my computer can do. This is what we do with programming languages. You to guarantee that 2 programming languages are can solve the same problems, there isn't some problem you can solve with Java that you can't solve with C++. And the way that we prove that is both those languages are Turing complete. And so you can compile your Java to C++ and you can compile your C++ to Java. It's possible to do.
In a sense, compile them all to a Turing machine.
Well, there isn't really a Turing machine programming language.
Too bad.
Because there's no, this is the way you have to do it. It's just, if this can do it, then it's Turing complete.
Okay.
Yeah, compilers is a fun course.
Well, we deal with all the same problems in our memory, constantly having to make sure that we have enough space to not get into other people's memory space and things like that.
Oh, yeah.
So I know very little about it, but do computers, when machine language is actually running through the bytecode, is it a similar idea where it has a pointer and it goes through and has essentially a function where it says, here's what you do when you run into this, like a Turing machine? Like a tape and a pointer? Not really.
Kind of. I mean, you do have random access memory, like the tape on a Turing machine.
Right.
And so a pointer does exactly what you're saying. It points to some object stored in memory somewhere.
The difference is it can haul ass to one location to the other, and if you had a number stored of like, the first pointer is 2 from the beginning, the other one is 2 from the beginning, the other one's 1 from the beginning, it would immediately jump to that location, not having to like scan through it slowly.
But if you're talking about how the actual computation works, like on your chip, then what that's doing is when it comes across a pointer, it's just going and getting the value at that memory location, putting it in a register on your chip, and then running it through your logic circuit.
But you could technically take your memory and string it out into a single tape.
Yeah, you could. But so your logic, I'm not sure if I'm explaining what you were actually wondering about. Your logic circuits on your computer, where it actually does a computation, it basically has a bunch of feeds in for each bit. Let's pretend that we're 50 years ago and we're using 8-bit software.
Okay.
Then everything that you pass into your ALU, your chip, is going to be 8-bit numbers, and so you send signals down each of those 8 things, and it's going to spit out some 8 bits again. And so when you come across some pointer, it just means go put that in the register, which is basically means get it ready to feed into the sync, and then you just run it through. And some other thing comes out, and you put that value in the register.
Okay. I've heard that pointers are really hard to program with in languages that use them.
C++ has a bad rap
That's what I
for being a messy language.
Yeah.
Same with C#.
And it is kind of a messy language because they force you to do a lot of your own memory management. But that's just a coincidence of C++. I mean, when I use pointers in Swift, there's nothing weird about it. So, and it's because Apple has a way of keeping track of memory for me, so I don't have to personally manage my own memory.
Which most higher-end programming languages do. And
Right.
they just have
C++
garbage
is for, yeah, other ones have garbage collection. Apple has what they call automatic reference counting, which basically means if there's no more pointers to this place in memory, Apple swipes that memory.
automatically.
Automatically.
behind The scenes. With
And garbage
C++
collection is
doesn't.
somewhat similar. C++ is meant for very low-level programming where you want to fine-tune manage your memory.
Is that valuable when you don't have a lot of memory to work with?
It was valuable when you didn't have a lot of memory to work with. The other place where it's valuable is where you're doing things that are very, very computation heavy. So if I'm doing some process that I know is going to take my computer, an hour to run, and it's a process that's going to do over and over again, it's probably worth it to go rewrite that program in C++ and see if I can come up with some efficiencies to turn it down.
To make it faster?
To make it faster, more efficient, yeah. So there's advantage, and the advantage
So
is
C++ is known for being a fast language.
Oh, yeah.
yes, that's why people use it, and that's why it's still heavily used with like graphics, gaming. Game developers still use it a lot because of graphics. Now it seems like they're kind of getting away from that. There's you can kind of make up for it with just having a more powerful computer.
Right.
But I think your really heavy-duty games that are just cutting edge are still going to be using C++.
The majority, it seems like high-end languages are built on top of C++.
Yeah, a lot of times they're
JavaScript, PHP.
Built on top of it.
Lots of machine learning. You might write it in.
Apple's initial language was called Objective-C. It wasn't built on C++, but it was built on C. C++ is built on C.
Right.
So it was also built on C.
Well, C also has that same feature where you manage your memory, right?
Right. C++ you can literally build it from C. And so
There's a lot of problems they solve. Like if you're trying to create an array and fill it full, a lot of the higher end systems will automatically duplicate your memory capacity to fill up that array.
right.
But if you're literally down there in the C++ or whatever, you actually have to say, I want this much memory for this array before you actually start filling it up. Otherwise, you're going to start smashing into other
And so with most higher end languages, what they do is anytime you exceed the memory capacity of that array, they automatically just double its length and stick it somewhere else in memory.
Yeah.
Right.
Okay. So we talked about multi-tape Turing machine. Now, little corollary that falls from this basically for free. Now we can prove that a language is Turing recognizable if and only if some multi-tape Turing machine recognizes it. All right, let's prove this way first. Observe that a Turing machine is already a multi-tape Turing machine with one tape.
Oh yeah.
So that proves one way for us for free. Then the converse is proved by our previous problem. So we already know what a multi-tape Turing machine can do, what a Turing machine can do. We showed right here that a Turing machine can do what a multi-tape Turing machine can do in terms of recognizing a language. Notice that we never said anything about rejecting, just accepting.
Right.
Well, I guess we just said simulating.
Well, if they're logically equivalent, then isn't it also for rejecting?
I think so with this one.
Okay, so any multi-tape.
Now it makes me want to go double check what that says. But for sure recognizable. I mean, that statement's definitely not wrong. All right, let's switch over to this next board. I think that sees it all. Maybe back a little more.
The examples of wireless, for instance, garbage collection, of finding out, oh, there's nothing pointing to this, get rid of it, isn't always where it works, is because you can have three things point to each other, and there's no way for it to know that there was a circular reference point, and it will,
So it doesn't ever collect that.
it never just
Yeah.
get rid of it until the process completely terminates. And that can be a problem when you're running for hours, and it's just slowly building up these pointers, so you have to be careful with that.
Yeah, circular references.
But is that a big issue? It doesn't seem like a big problem unless you have a lot of it.
I've run into
it-
those problems.
It can run into problems. It can be a big issue. It's a problem I've literally had to solve a few times. Like on our app, someone keeps going back and forth between screens. And somehow we got a circular reference with one of those screens. Well, we don't actually store a screen in memory when you go back and forth on your phone. We generate a new screen every time you switch.
Okay.
And so it was just building up in memory all those screens. And maybe those screens were also doing processes, like some calculation.
And so they continue to do that.
And so, yeah, they continue to do that, building up. And yeah, it can turn into a real problem.
But sometimes it's good to just shut the whole damn thing and throw it out again.
So, yeah, you probably noticed it sometimes with an app. Just if you leave it open for a long time, it's slowly becoming worse and worse and worse and worse.
Video games do that too.
That could definitely be the problem.
Mm.
And so, force quitting it is basically swiping the memory. So that's one of the reasons that works. Anyways, last way that we might think we can make a Turing machine more powerful. And that is by making it non-deterministic. So maybe now we give our Turing machine a choice as to what it does when it reads a symbol. So when it reads a 0, it has a choice with replacing it with an X and moving to the right, or replacing it with a Y and moving to the left. We give it an option.
Isn't this basically going to be the same thing as how we model non-deterministic finite automata?
It's non-determinism. It's non-deterministic in the same sense.
That's what, yeah. And so
Yeah, but remember that a non-deterministic push-down automata was more powerful than a deterministic push-down automata. So a non-deterministic finite state machine and a deterministic finite state machine, logically equivalent. Non-deterministic push-down automata and a deterministic push-down automata, different. The non-deterministic one is actually more powerful. Now we're on the Turing machine level. Maybe a non-deterministic Turing machine is actually more powerful than just a deterministic Turing machine.
Will you remind me why that was the case for push-down automata?
No,
Okay.
because we didn't go over why it was the case.
We just said it was.
Because dealing with dealing with deterministic pushdown automata is weirdly complex. They're kind of hard to reason about compared to a non-deterministic one.
Really?
Yes. Now you're interested in them for compilers, for building programming languages, because you use, when you build a programming language, the grammar that you use is going to be one of those pushdown, a deterministic pushdown automata. You're going to use deterministic pushdown automata, things that are logically equivalent for a lot of your programming grammars. And they're very useful. They behave very nicely in terms of application. But talking about them theoretically is much harder. And so we skip over them for the most part. Just because the payoff for how complex they are to talk about isn't really worth it.
Okay.
So yeah, can't give you intuition for it. But so let's go back and remind ourselves of a non-deterministic pushdown automata. A non-deterministic pushdown, not a non-deterministic pushdown automata, non-deterministic Turing machine. That's what we're talking about now. So in non-determinism, we have a choice. And so, we didn't refresh on configurations, did we? Do you remember what configurations are on a Turing machine? So looking back over at the Turing machine that we had over there in the beginning, so at the very start, it started with the input string 0, 0, 0, 0, 1, 1, 1, 1, right?
Yeah.
And we called, let's call that first state Q naught. So the first state is Q naught. So here's how we represent its configuration. Q naught is the state that it's in. Here's what the tape currently looks like. And our state comes right before the symbol we're currently reading. So when we started out that machine over there, we started out reading the first 0, and our string started out looking like this. After one step of the computation, what's the first thing we did? We took the first 0, we replaced it with an X, and we moved to the right. And let's call that next state there Q1. So the way we would represent that is we took that first 0, we replaced it with an X, we moved to the right, so here's Q1, and then we still have 0, 0, 0, 1, 1, 1, 1. That would be our next configuration.
Why is the key shift places?
It always comes right before the symbol we're currently reading, so that you know which symbol is being read next. And then the next step of computation, we stayed in state Q2. We read 0 and moved to the right. Or we stayed in state Q1, but we read 0 and moved to the right. So that would be X, 0, Q1, 0, 0, 1, 1, 1, 1. Right?
So every time a symbol changes.
We read 0 and moved to the right.
What? But that's not Q2, that's Q1.
It's still Q1 because look, we don't change state.
Oh, okay. Yeah.
Yeah, this right here is Q naught. This right here is Q1. And we didn't change state when we moved to the right.
Right.
We don't change state until we replace 1, da da da. Anyways, if we were to continue this process, dot, 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 on forever, our final configuration would have looked like X, 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 Y, 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 and then Q except. Right?
Mm-hmm.
Or something like that. Maybe the Q except would have been shifted one to the left. I don't remember what we did at the end. But it's going to look something like that. And then that was our accepting configuration. If you start with this configuration and follow the steps of that Turing machine, you have to go through all these configurations to this configuration. There's no choice about it. It's deterministic. Right? Now, if we gave it a choice, then it doesn't necessarily have to go from this configuration to this configuration. It could have gone up to 3 possible different configurations, or 5, or 10, or however many options we gave it, right?
Mm-hmm.
So that's what this tree here is meant to represent. Each of those nodes represents a configuration. So we start out with this configuration, and then we have some choice about which configuration to generate next. We could have done one transition which did that configuration, one which did that configuration, one which did that configuration. And from this configuration, we have a bunch of options, right? And our non-deterministic machine accepts if any of these branches, if we follow these out forever, if any of them ever produce an accept configuration, a configuration that had an accept state in it, then our non-deterministic machine accepts. So you think about it as generating all these branches in parallel. If any of those branches ever leads to an accepting configuration, our non-deterministic machine accepts. Make sense? Okay, and you just come to the transition function. You probably could have guessed, but let's specify what the transition function is. The transition function, it takes a state and an input symbol, and it moves to all the possible state input symbols and left or rights that you could have gotten from this one. Right? And all the possible ones is going to be subset of the power set of all the things that can be reached from that. It's almost identical to our transition function for a non-deterministic finite automata. Going back to our very first non-deterministic finite automata, its transition function looked like this. Oops, wrong delta. This kind of delta. It was Q cross sigma, and it spat out the power set of Q cross sigma. So, almost identical, right? Anyways, so there's our transition function. Now we're trying to simulate our non-deterministic Turing machine with a regular Turing machine. Now let's not make life hard for ourselves. We already know that a Turing machine is logically equivalent in terms of recognizing a language to a multi-tape Turing machine. So I'm going to use a multi-tape Turing machine to show that I can simulate a non-deterministic Turing machine. Does that make sense? So that's why I'm using a multi-tape Turing machine here. Now here's our strategy. I'm not going to bother writing out a proof similar to the one there because it gets kind of wordy. So I'm just going to try and give you the idea for what we do. So we build 3 tapes here. We have 3 tapes. The first tape is going to read the input that we're trying to read, and it's going to keep that input forever. This tape never changes with the input. It just gives us a place that we can always go back to get our initial input to start again. Good on that one? Our second tape here is going to be our simulation tape. So it's going to start by reading this input and then performing all the operations on the input to generate some configuration. So it's going to be the one responsible for taking this configuration and going to the next one.
So
Or taking this configuration and going to this one.
is there a tape for each different branch?
No, only 3 tapes. This final tape down here we call the address tape. It's going to keep track of which options the simulation tape should use. So when the simulation tape starts out here, it needs to know, am I supposed to use this transition, or this transition? It's going to look at our address tape, and our address tape is going to have 1, meaning on the first choice, choose 1. 2 would mean, when you come down here, choose the second option, so not that one, but this one. And then 1 would mean, choose your first option again, so it would say, you're going to do this configuration. So it's guiding it down this path. With me so far?
So how does that... So this is essentially, this is modeling something that will accept or reject, right? But
We are trying to simulate running through all these configurations.
But that doesn't run through all the configurations.
Well, we'll explain how it runs through all the configurations here in a second.
Okay.
So when we start out, the simulation tape is going to start out blank. This is going to start out with the input, and this is going to start out with just 1. And we'll assume that we're looking at this tree over here. What do? We are going to start with this input. So I take this tape, first thing I do is write 0, 0, maybe do an example of it here. I'm going to do 0, 0, 0, 1, 1, 1. I started with that. Then I look at my tape here, and the first symbol on this tape is a 1, which means I perform whatever this first configuration step was, that transition. And maybe that first transition just replaces 0 with an X. And so that was going from this configuration to this configuration. You with me?
Yeah.
Okay. I see. Is this in an accept state? No, it's not in an accept state. Right? So we barely we checked this one. This one we found out. Get rid of that. We'll come back to it. We found out this one's not an accept state. So we know that one's not an accept state. And of course we would check our initial configuration, make sure that's not an accept state. If the initial configuration was accepting, just accept. So first we check that one, now we've checked this one. So then, when we check that, we come back here, we erase this tape. we reset it back to 0, 0, 0, 1, 1, 1, whatever the input tape had. Remember, we never changed this one, so we can always get that number again. And I come down to this number, and I increment it to 2. You with me?
Not really.
These were all the possible configurations for our non-deterministic Turing machine.
Right.
Right? So, let's go back. This first configuration is just a starting configuration. That's just your input string with your start state, right?
I'm not making the connection between your diagram and an input string.
So this right here is representing all the configurations.
Those are representing.
So this right here is what this is. This node is the first configuration.
And then the next 3 nodes below it are different possible configurations.
Different possible configurations. For a deterministic machine, there's only one thing we can do when we're in this configuration, and that's to go to this one. Because that Turing machine over there is deterministic.
Right.
But there might have been some choice where we could have also, instead of that, we could have done something like replace it with a y, q1, 0, 0, 0, 1, 1, 1. So maybe we could have gone to that or to that.
Right.
So that's what this is representing. We're pretending that we had 3 choices from the initial configuration. Right? So let's reset. We start out a 1 there. We start out that with just our input string, and this with our input string.
So the 1 is representing you are in the first configuration.
Actually, we can start this out with a 0. Let's start that out with a 0.
So you're at the very top.
So we're at the very top. So what do? We populate this with the input string. So our simulation tape is one that we're always changing. This one we just increment down here. This one we're always changing. So start that out with the input string. Then I look at this to figure out which operation I should do. This says a 0th operation. We'll interpret that as don't do any operation. Now check, am I in an accept state? Is this an accept state? No.
Okay.
So once I get that that's not an accept state, I increment this to a 1 now.
So why do you change it instead of adding on to it? Aren't you trying to create like a pathway through the configurations?
Hold on. Watch the process of what we do now.
Okay.
So now I increment that to 1, reset. Here's my input tape. I reset my simulation tape with our initial starting string, right? And now since there's a 1 here, that means I take my first choice of what I could have done.
Oh,
So now I go to this configuration.
okay.
So then my input string, or my simulation tape, gets changed somehow based off of the new configuration. So now maybe it looks like that.
Each configuration is a sequence of...
It's taking one step in the machine. A configuration is just taking one step, going from here to there, or from here to there.
Okay.
It's capturing, I don't want to say the word state, but that's the best word for it. It's capturing the state of the whole process after one step.
Right.
And after every step, we have a new configuration that the whole machine is in.
Okay.
So that's what the configurations are tracking here. So then, this said, take the first choice on whatever those were. And so we did our first choice, and now our simulation tape looks like this, right? And we see, is it accepting?
No.
And if it's not accepting, then we say, okay, that's not an accept state. And we switch this to a 2. We increment it.
Okay.
Now, that's a 2. We reset up. That's going to be 0, da, 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 da. Maybe the second configuration was replacing this with a y. When we came down this way. And we say, is that an accept state? And if it's not an accept state, we cross it out. And now we increment this with a 3.
Okay.
And we restart. And so now we check this one, and we see if that's an accept state. If it's not, then we come back and we increment this. Now what we had to do beforehand is know the max number of children that we could do. We're basically just keeping a memory address of this whole thing. And so now, after that, when we increment again, once we get past 3, pretend that we somehow knew 3 was our cap. Like, it doesn't make sense to put 4 there, right?
Right.
Now, how we would know that it doesn't make sense to put 4 there, we'll kind of ignore that detail for now to get used to this. But let's pretend that we somehow knew that we can't increment past that.
Okay.
So then I would increment this. It's the same way that we count. Once we get past 9, how do we count now? We go to 1, 0.
Right.
And so now I'm going to go to 1, 1.
And then 1, 2, 1, 3.
Right, and so now we go 1, 1, check this one. Nope. Now we go 1, 2, check this one. Nope. Now we go 1, 3, check this one. Nope. And then we check this one, we check this one, we check this one, da da da, keep checking across, and eventually we're going to come down here to one that's actually an accept state, if there is one.
Right.
And then we'll accept. So now, for more programming language, here's what we're essentially doing. We're looking at this tree for our non-deterministic Turing machine, and we're just doing a breadth first search, looking for an accept configuration. If we tried to do a depth first search, we might be diving down infinitely far, so we can't do a depth first search. We're just doing a breadth first search. Make sense? So if this thing over here does have an accept state somewhere, then our process will eventually find it. Make sense?
Mm-hmm.
Now, if it has a reject state somewhere, we don't care. We're only saying that this machine will accept when if this machine over here accepted. That's all we're saying.
So really, each one of those nodes is associated with a specific address, and then your machine is incrementing.
This is keeping track of the address that we're checking to.
Right.
These nodes are representing possible configurations that our non-deterministic
But
machine could be
each
in.
one of those nodes has an address.
Yeah, well, you can make up an address for them, right?
Right.
And I just picked a random way of talking about an address, but that's all that really matters. We just have some address for all those, and we check each of those addresses in a breadth first search way. So yeah, there's an infinite number of ways we could have done this. That's just one way to do it. And that's the idea behind it.
Okay.
Okay. So that is non-determinism. So these Turing machines that we're talking about are we call it a robust definition. They're very robust, meaning that we can't find something to add to it to somehow make it something new. It seems like no matter what we throw at a Turing machine, it's still just a Turing machine. And so yes, today we have no notion of anything that computes that's more powerful than a Turing machine, that can fundamentally solve problems that a Turing machine can't solve. And so if you come up with something, you'll be very famous. Okay, now,
Wait, so
Go ahead.
my question. If you're thinking about it mathematically and not as a Turing machine as an actual computer, what if you have an infinite number of tapes rather than a finite number of multiple tapes?
so an infinite number of tapes would give you something new, probably.
Would that solve any, I mean, I guess, I don't know if you have the answer, but would that solve any more problems than the regular Turing machine could?
Maybe, but it no longer captures what we intuitively mean by an algorithm. So roughly kind of jumping ahead to the Church-Turing thesis, what Alan Turing and Alonzo Church were doing, were trying to come up with some way of defining what people meant by algorithm. Because people would talk about algorithms all the time. Talk about something like Euclid's algorithm.
Right.
And it seems like what they meant is some finite procedure for generating some result.
Mm-hmm.
And so they were limiting themselves to finite procedures. And so an infinite number of tapes that you're processing infinitely many times is already breaking that intuition for what they were after with an algorithm.
But as a field of mathematics, it makes sense to investigate that.
Maybe, but it's no longer capturing that intuition of what we meant by an algorithm. And that's what they were after.
Well, it loses its practicality when you go that far.
It loses its practicality, but
So does an infinite tape, but
Well,
not really an infinite tape, just an arbitrary amount of memory. You never actually use infinite memory. Why do you never actually use infinite memory? Because your machine does a finite number of processes. We just think about letting it run arbitrarily long. If we have our machine here looking for an accept state, it never checks all the states. We're just guaranteed that if there is an accept state in there somewhere, it will eventually check that state.
But you could say though that an infinite number of tapes, or an infinitely long tape and an infinitely number of tapes would be is technically proven to be the same thing.
No, we didn't prove anything with an infinite number of tapes. When we talked about a multi-tape Turing machine there, it was presupposed that K was finite. Because one of the first things we need to do is we need to read the tape from left to right, reading all the input. You can't read an infinite number of input. And it also makes our state control for our Turing machine has to be infinite. Because the way we were tracking our input was, we kept a state for every possible combination of inputs you could have read. If you're reading an infinite number of inputs, now you need an infinite number of states. We don't allow that with the Turing machine. Turing machine still has a finite number of states. It's just that the tape is infinite. So yes, adding those things is something different, but it's now running away from what we mean by an algorithm and what we mean by computation. Intuitively, because we already had intuition for what these things were. Now we were looking for precise definitions that captured those things. Anyways, jumping now to an enumerator. What's an enumerator? An enumerator is basically the same thing as a Turing machine, but it starts out with a blank tape, so you don't give it an input. It starts out completely blank tape. It has no accept state. Instead, it occasionally goes to what it calls a print state, where it prints everything on its tape up to some special location, like the head. You can think about it as up to the head and we'll be fine. So E has inside of it a special print state. If it ever goes into the print state, it prints everything to the left of the head. So an enumerator is a Turing machine. The tape starts out blank, and then you just start it running. And as it starts running, it starts manipulating the tape. Occasionally, it will go into what we call a print state. Anytime it goes to a print state, it just outputs whatever's to the left of the head. And so this thing could have been going along and printed out an AB, and then an ABB, and then a da-da-da, and then a da-da-da, and it can print out an infinite number of strings. Remember, with a Turing machine proper, what did we do? We gave it one input string, and it spit out yes or no, accept or reject. Or it ran forever, but if it was a decider, it spit out yes or no, accept or reject. This thing, we don't feed it a string and have it tell us yes or no. We just turn it on and let it start running, and it just starts spitting out strings. So this is a generator, not a recognizer. It generates strings. It doesn't tell you yes or no to a string, it just generates them. It's kind of like a regular expression. When I did the regular expression, A star, B star, that just generates a bunch of strings. It's not saying yes or no to a particular string. A finite automata, that said yes or no to a particular string. A regular expression, that generated strings. So this is kind of like the regular expression version of a Turing machine. Kind of. Make sense? Okay, so that's what we call a numerator. This is kind of a wordy definition. It's not a proper definition, but just giving you intuition for these things. So a Turing enumerator, from here on out we'll just say enumerator, is a deterministic Turing machine with a printer. It starts out with a blank tape and can print strings, W1, W2, ... possibly going on forever. It is a generator, not a recognizer. So it's like a regular expression or a grammar. It generates strings. It doesn't accept strings.
Does it matter if it's deterministic or non-deterministic? So the same thing, I mean,
It shouldn't matter. I don't think it matters. The deterministic one's just easier to reason about. Okay, so now a language is Turing recognizable. Remember, what's a Turing recognizable language? It's a language that a Turing machine can always say yes to everything in the language. It might not be able to say no to things not in the language, but it will say yes to everything in the language. So a language is Turing recognizable if and only if some enumerator generates or enumerates it. If some enumerator can enumerate that language, it's Turing recognizable. And if a language is Turing recognizable, some enumerator can enumerate the language. And that's what we're going to prove. Make sense? So let's go over the proof. Let's prove it this way first. Let's prove that if an enumerator can enumerate the language, then a Turing machine can recognize the language. So assume we have some enumerator, and it enumerates this language. It just starts spitting it out. When you turn it on, it just starts spitting out all these things, printing out all these words. We're going to build a Turing machine that recognizes all those words. With me? Yeah? Okay. So let A be the language of the enumerator E. Now we're going to define some Turing machine to recognize A. Let M be the Turing machine that on some input W, it will just run E, turn on E, let it start printing out strings, and compare each of E's outputs, each of E's strings, with W, the string you gave it. And it will accept if they're ever equal. Does that make sense? Let's pretend I'm the Turing machine, and I've got some enumerator here that spits out a bunch of words. You give me a string, and you say, is this string in the language? So you give me the string, I turn on the enumerator, and start spitting out words. I just compare that string to all the words the enumerator spits out. If I ever see the word, I say, yes, it does. What if I don't ever see the word? Well, I only promise you that I will accept if the enumerator eventually generates a string. We were only doing Turing recognizable, not decidable. Make sense? Cool. So then M recognizes A. Okay, now let's go the other way. Let's show that if a Turing machine recognizes some language, then I can construct an enumerator that enumerates that language. Make sense? Okay, how do we do that? So let A be the language of some Turing machine M, be the language recognized by some Turing machine M. All we're guaranteed is that the Turing machine can recognize it, not necessarily decide it. Okay, so let A be the language recognized by some Turing machine M. Let sigma be the alphabet of the language A, and let S1, S2, ... be the listing of all the strings we can get from that alphabet, generated in some order, like a lexicographic ordering.
What does lexicographic mean?
It's just a standard ordering of strings. So you order them alphabetically and by length. So let's do an example. Let's pretend that A here was 0 to the n, 1 to the n. You with me? So then our alphabet is what?
0 and 1.
Just 0, 1. So our alphabet star is all the possible binary strings you can generate. Right?
So like empty 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1.
Perfect. Exactly right. So it'll be empty 0, 1. 0, 1. Or sorry, 0, 0. 0, 0, 0, 1, 1, 0, 1, 1, ... continuing on. That would be listing all the strings out in lexicographic order.
No, and particularly the n, the same number of zeros, the same number of ones. Is that?
Listing it out. So if we're talking about this language, 0, 1, star, or sigma star, all the binary strings, and if I list those out in lexicographic order, my first string is going to be the empty string, and then it's going to be 0, and then it's going to be 1, and then it's going to be 0, 0, and then it's going to be 0, 1, and then it's going to be 1, 0, and then it's going to be 1, 1, and it's going to be 0, 0, 0.
I was thinking all the accepts, but that makes sense now.
Okay. And we can go on this way forever, and I'd list out every possible binary string. Right? So that's what S1, S2, ... is here. It's some listing out of strings like this. Good? And don't get confused by the scratch work. This was scratch work. Okay. So, let's try it again. Let A be the language recognized by some Turing machine, something like 0 to the m, 1 to the m. Let sigma be the alphabet of A, something like 0, 1. and let S1, S2, dot, dot, dot be some listing of all the strings in sigma star, like lexicographic order. So that would be like this. Here's S1, S2, S3, S4, dot, 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 etc. Good? Now what do? We're defining our enumerator E, which will enumerate all the strings in 0 to the n, 1 to the n. That's what E is going to do. How does it do that? So let E equal, parentheses, first thing we do is ignore our input. It's an enumerator, don't try and give me input. I'm an enumerator. So ignores any input you give it. And it's just going to repeat steps 2 and 3, changing our value of I. So I is going to increment. It's going to start out 1, then 2, then 3, then 4, dot, 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 dot. I goes on forever. What are we going to do in step 2? We run our Turing machine M for I steps on the first I strings. If our Turing machine M accepts any string, S sub j, any of those strings, S sub j, then we print it. So let's make sense of that. Get some scratch space here. So let's pretend we have our Turing machine for 0 to the n, 1 to the n. Now the first thing my enumerator E does is it plugs in the empty string, and it plugs it in and it allows M to run. So here's the string I'm plugging in, here's S, and here's number of steps. I let the machine run. So I run the empty string into the machine for 1 step. Does it accept? Looking at that exact machine over there. I run the empty string on it for 1 step. No, it doesn't accept, so I don't print out. Okay, what do I do next? I run the empty string on it for 2 steps. Does it accept? No. Now I run 0 on it for 2 steps. Does it accept? No. So I don't print out either of those. Now I'm going to run the empty string on it for 3 steps. I'm going to run 0 on it for 3 steps, and I'm going to run 1 on it for 3 steps.
I'm not understanding why that's the case.
And then after that, I'm going to run the empty string on it for 4 steps, 0 on it for 4 steps, 1 on it for 4 steps, and then 1, 0 on it. Oh wait, 0, 0 on it for 4 steps. We're almost there. Then I'm going to run the empty string on it for 5 steps, 0 on it for 5 steps, 1 on it for 5 steps, 0, 0 on it for 5 steps, and then 0, 1 on it for 5 steps.
Then it accepts it.
0, 1 on 5 steps, does it accept it?
Yes.
Maybe not. Maybe it needs like 10 steps to accept it. I don't know if it accepts it in 5 steps. We could count. Maybe it does, maybe it doesn't.
Okay.
I see.
But if I kept listing this off,
You'd eventually get there.
dot, 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 I'd eventually be listing 0, 1 here with something like 10 steps. In that case, it would accept. And so once I did that, my enumerator would finally print out its first string, 1, 0. That would be the first thing it printed out. Now eventually it's going to print out, it's going to go along, and it's going to do 0, 1 with 11 steps. So I was going to print out 0, 1 again. Or 0, 1. So it's going to print out 0, 1, and it's going to print out 0, 1 again. So this string is going to get printed out over and over again, but eventually we're going to get down to 0, 0, 1, 1 with something like 50 steps, and then it's going to start printing 0, 0, 1, 1. You see that? And eventually every string that our Turing machine accepts will eventually be printed out by this enumerator with enough time. This is stupid and efficient, but will it eventually do it? Yes, that's all we care about. So that's how we create an enumerator that can recognize the same language as a Turing machine. Make sense now? Okay. And that gets us to definition of an algorithm, and that's probably a good place to start next time. Because that's the next section, the next chapter. Did we finish? Oh yeah, then enumerates. You have any questions before we call it for today? It's too bad because we're getting to the fun stuff. All right, we'll upload it.